So exponential functions they're very nice because no matter what kind of exponential function you have, they're all more or less the same. So an exponential function is one that looks like y equals a times b to the x. Or, if we use function notation, f of x equals a times b to the x. And what makes this different from the functions that we've been talking about so far is that x, our variable, is an exponent. So that's why we call it an exponential function. Any exponential function is going to look something like this. And for all the exponential functions that we are going to work with, b, the base of the exponent, b is going to be greater than 0. So we're always going to have a positive number that we're raising to a power. So this, we're never going to raise, this b is never going to be a negative number. It's just, we're always going to have a positive number that we're raising to a power. Yes?
Is that just what we're doing today, or is that always the case?
For pretty much any exponential function you work with, you're always going to work with a base. The base is always going to be 5.
So like on the test, there won't be a negative base?
Pretty much for anything you do in math ever, there will never be a negative base. And the reason for that is if we think if we have a negative number, if your exponent is even, you get a positive answer, but if your exponent is negative, you get a negative answer. So if your base, if this number is negative, then weird things happen with your function. So to keep weird things from happening, we're always going to have our base, this whatever this number is, always going to be positive. Another nice thing about exponential functions is their graphs always look pretty much the same. So if I were to sketch a graph of, we'll say y equals 2 to the x. Well, my graph for y equals 2 to the x looks like this. And pretty much any exponential function is always going to look like that. And we'll talk about how we make these graphs in just a minute. If we have a fraction as our base, so y equals 1/2 to the x, anytime we have a fraction as our base for our exponent, our graph is going to look more or less like this. So anytime we have a fraction as a base, our graph looks something like that. Now I want to sketch one more graph. If you see something like this, y equals negative 2 to the x. This does not mean negative 2 raised to the power. This means negative and then 2 to the x raised to the power. So y equals negative 2 to the x. we do the exponent first and then make whatever we get negative. And that graph, anytime we have something like this, that graph is going to look more or less like this. So remember, when you see something like y equals negative 2 to the x, it means this. We're not raising negative 2 to the power. We're raising 2 to the power and then making whatever we get negative. Yes?
Is that whenever you have a negative?
Yes. When we have a negative in front of this, we do the exponent first and then the negative. Using PEMDAS, we always do the exponent first. So any exponential function, if our base is positive, not a fraction, it looks more or less like this. If it is a fraction, it looks more or less like this. And we have a negative in front, it looks more or less like this. So that's another nice thing about exponential functions. Their graphs look pretty much the same. Are we good so far? So let's think back when we were graphing linear functions. If we had a table of values. So let's say I have an x and a y for my table of values. 1, 2, 3, 4. And the way we could tell if this was a linear function is we saw if we're adding a constant number to the x's and to the y's. So this is a plus 1, that's a plus 1, that's a plus 1, that's plus 2, plus 2, plus 2. And when we saw that, we said, okay, yes, this is a linear function. And we said the slope is the y over the x. The slope is 2 over 1. It has a constant slope. For an exponential function, we multiply the y values by a constant number. So that's how we can tell from a table of values if we have an exponential function. So for example, an exponential function would look something like this. And I'm going to start at 0 for this one. 0, 1, 2, 3, 4. I'll just do it at 3. 3, 9, 27, 81. So the x's are going up by 1s. That's fine. But the y's, I'm multiplying each y value by 3 to get the next y value. This tells us that this would be an exponential function. So that's how we tell from a table of values if something represents an exponential function. We're multiplying each y value by some number to get the next one. Where for a linear function, we add. good with the difference between a linear function and an exponential function from a table of values? All right, let's look at an example where we evaluate an exponential function. One place that exponential functions show up frequently is population growth. Population growth can be modeled with an exponential function. That's an extremely common place for exponential functions to show up. So let's say we have a population of, in a biology lab, you look at bacteria in a petri dish. We have a population of bacteria, and it's given by this exponential function, f of x, that's the population, is 2,200 times 2 to the x, where x equals the number of hours. So we plug in the number of hours, and we get the population of the bacteria in this petri dish. They're reproducing, the population is growing. And the question says, how many after 5 hours? Well, we would say that f of 5, when we're plugging in 5 for the number of hours, that's 2,200 times 2 to the 5th. Now, something to be careful of here, we need to follow PEMDAS. PEMDAS says we have to do the exponents first. So you can't multiply 2,200 by 2 and then raise that to the 5th power. So be careful there. We have to do the exponents first. Now, what I would suggest you do is in your calculator, let's grab our calculators, and we'll type it into the calculator exactly like we wrote it. So as soon as this comes up, so what I'm going to do is I'm going to say 2,200. Whoops, not 2,000. There, 2,200. 2,200 times, and then I'm going to put my 2 to the 5th in parentheses. So parentheses, 2 to the 5th power. And this way, the calculator will do this 2 to the 5th first, and then multiply. And I hit enter, and I get 70,400. This is how I would suggest you evaluate these exponential functions. Type it into the calculator exactly like it's written, but put the exponent part in parentheses. So if it helps you to think about it, put parentheses around the exponents. If it helps you think about it up here, put parentheses around the exponent part. And we get that after 5 hours, we have 70,400 bacteria. Exponential functions grow really fast. All right, we're good with evaluating this exponential function. So to graph an exponential function, we're just going to make a table of values by plugging in our exponential function to find our y values. So let's look at that. We want to graph y equals 2 times 3 to the x. Now, if it helps you remember, this is not 6 to the x We don't multiply first. If it helps you remember, you can put parentheses around there. We can't do the multiplication before we do the exponent. So we're just going to make a table of values. X, Y. And unless the problem tells you otherwise, for pretty much any graphing we do, you can make your table of values from -2, -1, 0, 1, and 2. Just use those points all the time, unless the problem tells you otherwise. So to get this first y value, I'm going to do 2 times 3 to the -2. And I'm going to put it in my calculator just like this. 2 times 3, raise that to the -2 power. And I get 0.22222. Here I'm going to do 2 times 3 to the -1. And I plug that in my calculator. And I get 2 times 3 to the -1 power. And I get 0.666666, repeating. It rounds it off here. Yes?
So we take the x value and put it to the power of the y to get...
Yes.
Okay.
So this is, I'm going to say 0.67. Just round it off to the nearest 100th. Here we get 2 times 3 to the 0. We can do this one without a calculator. What's 3 to the 0? 1. So we just get 2 times 1, which is 2. Here we get 2 times 3 to the 1. We can do that, right? 3 to the 1 is just 3. 2 times 3 is 6. And 2 times 3 squared. 3 squared is 9. 2 times 9 is 18. You can plug these in your calculator. You'll get the same answer. And let's check our work. Are we multiplying by a constant value each time? If we multiply by 3, if we multiply 0.22 by 3, we get 0.66666666, repeating. If we multiply by 0.67 by 3, we get 2. We multiply 2 by 3, we get 6. And we multiply 6 by 3, and we get 18. So that's a way to check to make sure you've done it correctly. Huh. It's 3 to the x, and the thing that I'm multiplying here by is 3. That's not a coincidence. Yes?
To make it an exponential function, do you always have to multiply with the y? Like, can it be multiplied by x and y be plus 1?
No, no. The y has to be multiplied for it to be exponential. All right, so let's graph this. And you can sketch a little graph. I have graph paper if you want to use it for your homework, but we can sketch a little graph. And I'm going to go by 2s on the y's. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18. So y to the -2 is 0.22. That's a pretty small number. That's going to be down here somewhere. At -1, x is -1, we get 0.67, which is a little bigger. And it's okay if we kind of guesstimate. At 0, we get 2. At 1, we get 6. And at 2, we get 18. So my graph looks something, oops, made my curve not quite steep enough. There we go. Something like that. This one grows pretty quickly. And we can see my graph looks more or less like these graphs that I sketched over here. 2 to the x is not quite as steep as 3 to the x, but they look more or less the same. Any exponential function is going to look more or less like this. Questions there? All right, so the main thing with the graphing is make sure that you do the exponent first before you multiply. You can put it in your calculator just like this. Your graph should come up looking like this, unless your unless your base is a fraction, and then your graph should come out looking like this. Or if you have a negative in front, it comes out looking like this. And your y values, you should be able to multiply by a constant number on your y's to tell if you have an exponential function. All right, questions? Okay. Our homework is in the book this time. This is section 7.6, and we're on page 457, and we're doing number 8 through 50, every other even. All right, let me stop this.